Okay, it's time to go ahead and get started. So today's lecture is going to be a little longer than the first lecture, and this is our agenda. We'll probably take a break because I don't think I'm going to have quite enough time to finish after 50 minutes. So when we get to the top of the hour, take like a 5-minute break, and then after that break, it's going to be much longer after that. And then there's an activity on today's lecture. And the activity, there's a handout, the activity handout on the table, and there should be enough for everyone, one per student. If not, because they got extras. And then at the end, we should have, maybe, well, it depends how long it takes you with the activity, but you should have some time at the end to work on Lab 0. Lab 0 is due tomorrow at midnight. Hopefully you have Vivado installed on your computer, or if you don't, you intend to use our computers in the back. This computer right here, on my previous section from page 11 today, don't use this computer because I don't think it installs correctly because it's not recognizing the board. I mean, you could use it and go as far as the simulation, but when you try to, well, actually, you can't even do that because it won't even have the board in the list of parts when you go to use Vivado at the very beginning. So anyway, just avoid that computer if you don't have your own. But the other 7 have Vivado, and as far as I know, they've been working. Okay. Again, if you don't finish the lab during class time and you have to use our resources, this is the door code. Okay, so as long as you can get in the building, you can get into this room at any time. And during the week, I believe this building is open till 9. I think it opens at 6 in the morning. It's open till 9 at night. On the weekends, Saturday, it's supposed to be open. I'm not sure about the hours, probably like 9 in the morning to maybe 3 in the afternoon, something like that. But I've been here on weekends. Like, in fact, I was here this past Sunday just for a short time, and I saw a couple of the doors open. So, technically the building is closed on Sundays, but most Sundays I'm here, I see at least one door open. So you can get in here during off class. So, okay, so also on each table, you should have this handout. This handout has some of the information we're going to talk about in class today, but use it as a reference. I would take a picture of this and keep it handy throughout the quarter. It has some basic gate symbols along with the truth tables that we're going to talk about. And then it has a bunch of theorems and axioms of Boolean algebra. Boolean algebra is just base 2 algebra. And when you look at these laws and identities, you'll see that some of them are the same as base 10, base 10 algebra, but there are some that are unique. Now, I'm not going to go through all of these. There's one in particular we're going to cover called De Morgan theorem. But like I said, this is more of a reference. Okay. Okay, so we're going to start with our basic logic gates. And the first logic gate we're going to talk about is the NOT gate. And each gate has its own symbol, okay, that identifies the gate. And the NOT gate symbol looks like this. Okay, it's an arrow with a little bubble. This is the input side, and this is the output side. And typically, we'll label the inputs and outputs of logic gates with variables. Okay, so for example, we could call input variable A. And if we call input variable A, then the output of this NOT gate would be symbolized like this in Boolean algebra. That we would show the same variable with a bar over it. Okay, this bar means opposites. So the input is A, the output is opposite A. And because we're talking about digital logic here, these inputs and outputs can only have 2 possible values, okay, either 0 or 1. So a way to describe the operation of a gate is to show what's called a truth table. And a truth table is just a table that shows what output you would get for all possible inputs. So since we only have one input to a NOT gate, okay, also by convention, inputs go on the left side of the truth table and outputs go on the right side. Now, these gates we're going to talk about today only have one output, but you can have, other circuitry that has, multiple outputs. And if you had multiple outputs, they still all go on the right. But anyway, here we just got a single input and single output. And because the values of these inputs and outputs can only be either a 0 or a 1, well, I only have two possible inputs. And if I have a 0 at the input of a NOT gate, I'm going to get a 1 out. And if I have a 1 at the input of a NOT gate, I'm going to get a 0 out. And remember, we call these zeros and ones, we call them bits. Okay. Now, I might have mentioned this last time that I used to teach for the EE department. And when I taught for the EE department, I mainly taught circuits classes. I also taught this class. But since I switched over to CT, I switched over last year, I've just been teaching CP classes. But I've taught circuits for many years. So I just mentioned that because if you have circuit questions, outside of lecture, this is a circuits lecture, I can help you with circuits. But occasionally, just because I'm kind of like a circuits person, I like to talk about circuits a little bit. So here, I'm just going to briefly go tangential from our material and talk just a little bit about circuits. None of this is testable, but I think it's useful to know because at the very least, it shows you how, your EE class, your circuit class kind of ties in to this class. And that's what these zeros and ones are all about. We talk about having inputs that are 0, inputs that are 1, outputs that are 0, outputs that are 1. Well, the 0 and 1 notation that we use in this class is just shorthand for voltage. How many people have had a circuits class? I think it's quite a few. I think there's quite a few EEs in this class. But don't worry, if you didn't have a circuits class, don't worry, this isn't testable. But if you had a circuits class, that's like the first day of the circuits class. You learn about what current is and voltage and resistance, right? So you see, ideally, a 0 is typically 0 volts. And ideally, a 1 is some plus amount of voltage, usually 5 volts. Okay, now that's the ideal. Those are the ideal values. Now, I imagine, especially here at Cal Poly, if you had your circuits here at Cal Poly, you've also had a circuits lab, right? An EE lab. How many people have had an EE lab? Quite a few. And if you've had an EE lab, you've probably made a voltage measurement, right? You use like a multimeter, you choose voltage, and you measure voltage in a circuit. Well, when you measure voltage in a circuit, is that voltage typically a steady value for any significant amount of time? What usually happens when you make a voltage measurement? Does it stay steady, or what does it typically do? I thought I saw someone raise their hand. Have you made a voltage measurement? Is the number that you see on the voltmeter display, does it typically like have a value that's like real steady for a long period of time? No, what usually happens? Yeah, it fluctuates, right? It will change over time. For nothing else due to thermal energy, right? You put current through a circuit, the components heat up, and the voltage changes somewhat, right? And that can change the resistance, right? You got Ohm's law that relates the three together. Well, because voltage is often, a varying quantity, in actuality, instead of saying a 0 is an exact amount and a 1 is an exact amount like we do in the ideal case, in the actual case, we'll say that a 0 is a voltage that's below a certain amount. Okay, for example, 1.4 volts. And we'll say a 1 is a voltage that's above that same amount. Okay, so if you have a voltage in a circuit that's less than this 1.4 volts, we'll call that a 0. If you have a voltage that's greater than that 1.4 volts, we'll call that a 1. Okay, now this threshold amount that determines what's a 0 and what's a 1, that can vary based on the type of logic circuit you have. Okay, but this is a common common voltage that distinguishes between a 0 and 1. So anyway, like I said, this is non-testable material, but I just wanted to mention this because a lot of times in a class like this, students are like, oh, these zeros and ones, they seem very abstract. Okay. Again, they're just shorthand for voltages. All right, so any questions up to this point before we move on to the next gate? Okay, the next gate we're going to talk about is the AND gate. And the AND gate has this symbol. I'm going to call the inputs A and B, and I'm going to call the output F. And the Boolean algebra that describes the output of an AND gate is that if our inputs are A and B, well, A ANDed with B, you could write like this, okay, where there's nothing in between, just like when you show multiplication in base 10. Or you can show it like this, A with a dot. Okay. Now, what AND means is shown in a truth table. So here's the truth table for a 2-input AND gate. Now, notice this AND gate has 2 inputs. And again, these inputs are binary. Right? The inputs can either be 0 or 1. Now, if I only have one input, there's only 2 possibilities, right? That one input is either 0 or 1. Can you tell me how many possible combinations of zeros and ones I can have when I have 2 inputs? So I have 2 bits? 4, right? Because both could be 0 at the same time, or this one could be 0, this could be 1 at the same time, or this could be 1, this could be 0 at the same time, or this could be 1 and this could be 1 at the same time, right? So there's 4 unique possible combinations if I have 2 bits. How about if I had 3 bits? 8, right? Because if I had 3 bits, they all could be 0, or you could have this, or you could have this. See, I'm just counting in binary here, using 3 bits. Right? 2, 4, 6, 8, right? Counting in binary, this would be 0, 1, 2, 3, 4, 5, 6, 7. All right, so 2 bits, 4 possible values, 3 bits, 8 possible values. How about if I had 4 bits? 16. How about 5? Well, 4 is 16, so 5, 32. Because every time you add a bit, you double the number of values. Right? So 5, 32, 6 would be 64, 7, 128, and so on. So this is an important relationship to know in this class. And that's the number of values that you can obtain from a certain number of bits is equal to 2 to the power of bits. So, if you had 1 bit, 2 values, 2 bits, 4 values, 3 bits, 8 values, and so on. Okay, every time you add a bit, you double the number of values. You double the number of unique combinations of zeros and ones. Okay, you'll be using this relationship a lot in this class and any digital class you take. Okay. So getting back to the AND gate, when you have an AND gate, you only get a 1 out of an AND gate when all the inputs are 1. So you see, if we have a 2-input AND gate like this, only when both inputs are 1 will I get a 1 out. For all other input combinations, I get a 0 out. Okay. So this is a truth table for a 2-input AND gate, but it's the same concept if you have more than 2 inputs, because you can have AND gates with 3 inputs, 4 inputs, 16 inputs. You can have as many inputs as you want to an AND gate. And no matter how many inputs you have, all the inputs have to be 1 to get a 1 out. Only one of the inputs has to be a 0 to get a 0 out. Okay? All right, so do you have any questions about the AND gates? All right, let's go to the OR gate. Okay, OR gate has this symbol. More aerodynamic than the AND gate symbol is. And in Boolean algebra, the OR operation is represented with a plus sign. So you see the output of this OR gate would be A or B. So, we use a plus sign, but that doesn't mean we're adding. Just like here, that doesn't mean we're multiplying, right? This means and, which is what this truth table means. This means or, that symbol. And what we mean by the or function is shown in a truth table. So again, 2 inputs, so 4 combinations. And an OR gate, as long as at least one of the inputs is a 1, you'll get a 1 out. So you see, we'll get a 1 for these 3, and we only get a 0 out of an OR gate when all the inputs are 0. And again, this is a 2-input OR gate, but the same applies if there's multiple inputs. If you have a 16-input OR gate, it only takes at least one of those inputs to be a 1 to get a 1 out. To get a 0 out, all 16 would have to be 0. Okay? All right, so that's the OR gate, the AND gate, and the NOT gate. Now, any questions? Because I'm going to include a couple of gates that are not on that reference sheet. These gates are on the reference sheet. Okay, but now I'm going to go to 2 gates that aren't on the reference sheet. But before I do, no questions up to this point? All right, the next gate we're going to talk about is a NAND. And NAND is short for not and. And a NAND gate is equivalent to an AND with an inverted output. So the output of a NAND gate, okay, the Boolean expression, well, I'm ANDing the inputs together first. So at the output of the AND gate, I have A, B, okay, just like I wrote over here. Then that output AB gets knotted. So you see the Boolean algebra for a NAND looks like this. See, it's A and B ANDed because that's what happens first, and then the whole thing is knotted. Okay, so a truth table for a NAND is going to be similar to the AND gate truth table. It's just the output's inverted. So, and I only get a 1 out when all inputs are 1. NAND gate, I only get a 0 out when all inputs are 1. Okay, otherwise, the output's going to be a 1. So you see the output of the NAND is just opposite that of the AND. And that's because there's an inverter here. And the symbol for a NAND gate okay, that's the symbol of an AND gate. It's equivalent to this, but here's the symbol we use for an AND gate. Notice how it's the same symbol as the AND, but it's got the bubble. The bubble identifies that the AND gate output is being inverted, and that's what makes it a NAND. So they came up with this symbol by, they kind of squished the inverter symbol into the AND symbol and just left the little bubble sticking out. Okay? So any questions about the NAND? So what's coming next? NOR, right? Because just like you have a not AND, you can have a not OR. Yeah, you have a NOR gate, and that's short for not OR. So it's the same as taking an OR gate and inverting the output. So the output of an OR, you're first ORing the inputs. Right? So at the output of the OR, right, we have this same Boolean expression. But now for the NOR, this gets inverted. The whole thing gets inverted. So it looks like this in Boolean algebra. And then the symbol for a NOR, same idea. It's the OR with a little bubble on the output. Then the truth table for a NOR, well, it's going to be like the OR, but the output's going to be inverted. So in OR, I'll get a 1 out as long as at least one input is a 1. For a NOR, I get a 0 out as long as at least one input is a 1. See, the NOR truth table would look like this. See, I only get a 1 out of a NOR when all the inputs are 0. So, do you have any questions about any of these gates? Oh, I'm glad I put this up here because I almost forgot about it. On that same handout, this reference handout, this one here. On the back side, I just have a picture of an electronic circuit that's a NAND gate. Okay, so again, this is some circuit stuff. You're not going to be testing on it. But I just want you to realize that these symbols represent actual circuitry. Okay, so see this symbol of this NAND gate represents a circuit that has a transistor, a couple of diodes, and a couple of resistors. Now, this isn't the only circuit that can give you a NAND gate. There's other circuitry, but this is an example of a NAND gate circuit. And when you take your 300 level junior classes, the EEs, and I think in one of your new 200 level, or it might be a 300 level, I think you see it earlier as a CPE, you see some of this digital logic circuitry. Okay, so any questions before we move on to De Morgan's? Or actually, no, we're going to do De Morgan's next. So we've done all this. De Morgan's is one of the theorems that's on your reference sheet here. Any questions before we talk about De Morgan's? Everybody good? Okay, so if you look at this reference sheet, and remember, there's one at every table. The very bottom one, okay, row 15, is De Morgan's. See, De Morgan's has two parts to it. Okay, there's a 15A and a 15B. Look at 15A. Now, instead of variables A, B, like I'm using at the board, this reference sheet is using variables X, Y. But you should be able to tell me, looking at 15A, and looking at the left side of the equal sign, you should be able to tell me what gate that Boolean expression represents. It's a NAND, right? Because A and Y are being ANDed together. Remember, the dot means AND. Now, you don't have to put the dot there. You could just have a space, and it means the same thing. But you see A or X and Y are being ANDed together and then inverted. So that's what's on the left side. And De Morgan says, one part of De Morgan says, that a NAND, this is De Morgan's, so one part of De Morgan says that a NAND is equal to the expression that's on the right side of that equality in 15A. And look what the right side says. Or can you tell me what it says? Like, what is the right side of the equation? I didn't have that specifically written on the
Not X or not Y.
right, that the right side is taking an OR gate and ORing X and Y that have been inverted. So I can draw that Boolean expression the following way using gate symbols. I have an OR, right? Because the OR is the plus sign. And then I have X being inverted. And I have Y being inverted. Okay, so you see, one part of De Morgan says that a NAND gate is equal to an OR gate with the inputs inverted. Now we're going to prove this in a little bit, but let's look at the second part of De Morgan's, because again, De Morgan's has two parts to it. Okay, the second part of De Morgan's, that's the 15B. So looking at 15B, what's on the left side of that equal sign? That Boolean expression is what kind of gate? That's a NOR gate, right? Because X and Y are being ORed together, then the whole thing's being inverted. So the other part of De Morgan's is that a NOR is equal to what? Because what's on the left side of that equality? Not X and not Y what? What about not X and not Y? What's happening to them? They're anding them, right? Yeah, that not X and not Y are being anded together. So that would be an AND gate with inverted inputs. X, Y. This would be not X. Okay, so you see there's two parts to the Morgans. One says this, the other part says this. And I'll prove one of them to you. Because I think if you see one proof, you'll be able to do the other proof on your own if you needed to. Let's move this over here somewhere. Oops. Got caught on the outlet tower there. Let's see, we can probably move it a little bit more this way. Yeah, that should be good. Yeah, now we can see that moves. Okay, so we're going to prove just this one here. Well, the way you prove whether two logic circuits are equivalent is look at the truth tables, right? Because we know the truth table for an AND. We did that earlier, right? Here's our truth table for an AND. Well, if this OR gate with inverted inputs is the same as an AND, well, when I do the truth table for this, I should end up with the same. Okay, so let's do a truth table. Now, in this truth table, we got, well, I'm going to use A and B in the truth table, even though I have X and Y here. Is that okay? Just because we did A and B over there. So just imagine instead of X and Y, we got A and B here. So A, B, and then I'm also going to have a column for not A and not, right? Because here, well, actually, let's go ahead and change it and make it the same. So there's no confusion. Make this A and B. I already did A and B. A and B. And A and B. Not A. So on the other side of this inverter, we have not A. On the other side of this inverter, we have not B. And then those two knotted variables is what's being worked together. So in my truth table, I'm going to have A and B along with not A and not B on the input side. And then I'm just going to have, we'll call this F. Okay, so I use the same A and B values that I did for the NAND. 0, 0, 0, 1, 1, 0, 1. And then those inputs A and B get inverted. Right, so here we're going to have 1, 1, 0, 0. Here we're going to have 1, 0, 1, 0. And now those inverted inputs is what gets ORed. Right, and I only get a 1 out of an OR gate when when all inputs are 1. So I'll only get a 1 here, and the rest will be 0. Oops, I made a mistake, right? I'm sorry. With an OR gate, I get a 1 out as long as at least one of the inputs is a 1. So these will be 1, and I only get a 0 out of an OR gate when all inputs are 0. So I made a mistake there. Right? But now, if you look here, see the outputs of this circuit is the same as the output of the NAND. And that's what tells us that these are equivalent. Okay, so if you did the same thing, if you did the truth table for this AND gate with inverted inputs, you would see that you get the same truth table as what we did for the NOR gate. And you might want to do that on your own at some point. Okay, but this is proving the Morgans, but no matter what you're looking at, whether it's a theorem or just two circuits, random circuits. If you ever want to check whether two logic circuits or two gates are giving you or are equivalent, you just got to look at their truth tables and see if their outputs agree and they're the same. If they are, then they're logically equivalent. Okay, great. So everybody good up to this point? All right, we're doing good on time here. All right, the next thing. Okay, that was the Morgan. Now we're going to apply the Morgans coming up shortly. Okay, but that's what the theorem is all about, what the equality is all about. Okay, the next thing we're going to look at are various digital forms. And we're gonna start with the truth table. And we already saw some truth tables here for gates. But you can make a truth table, based on anything. You can take any word problem and turn it into a truth table. So the truth table that I'm going to make here has the following inputs. Okay, one input. Let's see, what did I use as variables again? One input. I'm going to use the variable C. I'm going to have an input variable G and an input variable E. Or not. Actually, that's S. I'm sorry. This input's going to be S. I'll explain what these represent in just a second. And then the output is going to be E. Okay, so first of all, since I have 3 inputs, and these are digital binary inputs, they can only either be 0 or 1. How many combinations if I have 3? 8. Right? Because again, it goes back to this. Right? Number of values you have based on bits, just take 2, raise it to the number of bits, that tells you the number of values. So all of these could be 0, or it could have 0, 0, 1, or 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Just make sure I didn't make a mistake. 2, 4, 6, 8. And I'm just counting in binary. And by convention, when we make a truth table, we'll put the inputs in binary order, right? So if you were taking these as a binary number, right? Say it's 0, 1, 2, 3, 4, 5, 6, 7. Okay? All right, now in this truth table, this variable C stands for chips, like tortilla chips. G stands for eggs. And S stands for salsa. And E stands for eat. Okay, so we're going to make a truth table based on my appetite for these ingredients, a combination of these ingredients. A 0 means we don't have that ingredient, and a 0 means for E means I won't eat it. A 1 means we do have that ingredient, and a 1 for E means I will eat that. Okay, so again, this is based on my appetite. It would be probably a different truth table if it was for your appetite. But the first row would be the same for everybody, right? Because if you have no chips, no eggs, no salsa, you're not going to eat, right? There's nothing to eat. So E here would be, okay, if there's just salsa, again, this is my appetite. I just don't like salsa by itself. So I wouldn't eat just salsa. Okay, just eggs, yeah, I like just eggs. Oh, eggs and salsa, that's one of my favorites. How many people like salsa with their eggs? Like scrambled eggs? Yeah, quite a few of this class. Best thing, you never tried it, try it. Very good, I'll eat that. Tortilla chips by themselves, sure. Tortilla chips, salsa, of course. Chips and eggs, tortilla chips and eggs, no, not for me. And yeah, all 3, I wouldn't eat. Okay, so here's a digital representation in truth table form of my appetite for these combination of ingredients. Okay. Next thing we're going to do is we're going to use this truth table to come up with 2 different forms of Boolean equations. There's a Boolean form called SOP, and I'll explain what the acronym means coming up. And there's also another form called POS. Okay, but we're going to start with SOP. And SOP stands for sum of products. And I'll explain where that name comes from shortly. And we're going to get the SOP for E. So we're going to write the SOP equation for the combinations that I would eat. So the combinations where the output is equal to 1. So when I'm writing an SOP for E, I'm just looking at these rows of the truth table, right? Because that's where E equals 1. And now, okay, let's look at this row right here, right? I'll eat when there's no chips, there's eggs, and there's no salsa. So when I write this equation, or when I write the term for this row, if there's a 0, I'm going to put not that variable. And where there's a 1, I'm just going to put that variable. right? Because a 1 means I have it, and a not means I don't have it, right? And a 1 means I have it, and a 0 means I don't have it. So you see this here, okay, looking at this row right here, I don't have chips, so I put not C. I have eggs, so I just put G, and I don't have salsa. And this is going to equal E. Right? So you see, I'll eat that combination, or I'll eat this combination where I don't have chips, I have eggs, and I have salsa. So everybody see how I get those two terms? Okay, because you saw how I get those two terms, the rest is just the same thing. Now, I'll also eat if I just have chips. That would be C, not E, not that. Or I'll eat if I have chips and salsa with eggs, right? So that's C, not C, that's. And again, if I make a mistake, point it out, okay? Right, so does everybody see how I get this sum of products, right? I'm just looking at where the output of the truth table is a 1, and then I'm just writing the term based on these inputs, right? If it's a 0, it gets a bar. If it's a 1, it doesn't get a bar. Okay? All right, so this is SOP, sum of products. Now, the reason it's called sum of products is because if you were to consider this equation as a base 10 equation, well, look, you got products, and then you're summing them. But this is not a base 10 equation, right? This is a base 2. So we're not multiplying here, we're anding, and we're not adding here, we're ORing. But because if you did consider this to be a base 10 equation, it looks like you're summing products. That's why it's called sum of products. In fact, you know, and is called logical multiply. And or is called logical and, or excuse me, logical adding. Okay, so any questions up to this point? Right, so this is SOP. There's another form, POS. Okay, POS is product of sums. Sometimes my U's look like B's. Product of sums. So we're going to get the POS for E. Okay, I wrote E as an SOP. Now I want to write E in POS form. Okay, now this is very important. Okay, you're going to see why this is true coming up, but just take my word for it that if you want POS for E, you got to start with SOP for not. Right? So you see, we want POS for E, but to do that, we got to start with SOP for not E. Like I said, just take my word for it right now, but you'll see the reason why in a little bit. So if I look at where the ones are in the output of my truth table to get what terms I have in my SOP for E, what do you think I do in order to get SOP for not E by looking at the truth table? I look at ones to get the SOP for E.
Look at the ones where E is 0.
Yeah, exactly, right? Because if we're using E for when E is 1, well, for not E, it would be the opposite. We look at where E is equal to 0, right? Because that's the case of not eating, right? So I'm going to have not E, and then I'm just going to do the same thing I did here, except I'm writing the inputs based on where the zeros are for the output. So I'm not going to eat if I don't have any of the ingredients, right? So these would all be knotted. I'm not going to eat if I just have salsa. Okay, I'm not going to eat if I have chips and eggs, no salsa. And I'm not going to eat if I have all three. All right, so did I do that right again? If I make a mistake, you know, just like anyone, sometimes it's very easy to miss a knot. So you always want to kind of double check. I didn't accidentally miss a knot or something. I think I did okay. But again, if I make a mistake, let me know. Okay, so this is SOP for not E. Okay, now the next thing we're gonna do is we're gonna do several steps here. Okay, you're gonna see that in just a bit. We're gonna use De Morgan's. And what I'm about to write, the reason I'm doing what I'm going to show you is to get POS for E. Okay, so I'm gonna show you the derivation of what we need to do to go from SOP for not E to POS for E. Okay, so the first thing we're gonna do is we're gonna knot both sides of the equal sign. So I'm gonna knot this side and I'm gonna knot this side. So what do you think this becomes? If you take a variable and you double knot it, that's like putting an input through two inverters. Yeah, it just goes back to what you started with, right? It's like double negative. Okay, so you see, that's gonna go away. You know, the knot bars are gonna go away, and I'm just gonna end up with. Okay, now the next thing, okay, and this is where De Morgan's comes into play. Can you see that if I look at this whole thing, right, this whole right side, can you see that if I take this as an input and take this as an input and take this as an input, take this as an input, can you see that this is a NOR gate equation, right? Because see, this input is being ORed with this input, which is being ORed with this input, which is being ORed with this input, and then it's all inverted, right? The only difference between this equation and what we wrote over here is that here we just had single variable input. Here we have an expression, you know, like multiple variables. But if you consider this to be an input, this an input, this an input, this an input, this is just showing a NOR gate, right? A 4-input NOR gate. You see that? And what does De Morgan's tell us? De Morgan tells us a NOR gate is the same as an AND gate with the inputs inverted. So I can take each one of these inputs, invert them, and then AND them together. So you see, I'm going to take each input, right? So not C, not G, not S, invert it, and then AND it with the next. So you see, this would be not C, not G, S, all inverted, ANDed with C, not G, not S, all inverted, ANDed with C, G, S, all inverted. So you see what I did? I took each of the inputs, I inverted them, and then I ANDed them together. That's exactly what De Morgan's tells us is the equivalency, right? A NOR gate is equal to an AND with the inputs inverted. Right, so you see, we did De Morgan's here. Okay, so does everybody see that? Okay. All right, now, okay, we're not to POS yet. There's one more step. Okay, look at this term. Look at this term. Look at this term. Look at this term. Okay, just look at that term right there. Can you tell me what kind of gate that is if you consider these to be inputs? Like we have input not C, input not G, input not S. That's a NAND gate, right? See, because we're ANDing those inputs together and then we're inverting it. See, that's just like what we have written here. The only difference is this was 2 inputs, that's 3 inputs, right? But do you see each one of these is a NAND gate? And what does De Morgan's tell us? A NAND is the same as an OR with the inputs inverted. So I look here, I take each input, invert it, and then OR it, right? So you see, this is going to give me C ORed with G ORed with S. then this is gonna give me C ORed with G ORed with not S. This is gonna give me not C ORed with not G ORed with S. And then this last one is gonna give me not C ORed with not G ORed with not S. And I don't, again, if I make a mistake, let me know. Did I get on the inversions right here? I didn't mess up with the bar or something. I think I got them all. But you see what I did for each one of these, since each one of these is a NAND, I took each one of them, used this part of De Morgan's where I inverted the inputs and then I ORed them together. Okay, well, look. This is POS, product of sums. So you could look, here's the sums, and then there's the products, right? The sums are getting logically multiplied. Now again, plus means or in base 2, and the dot means and in or 2. But if you were to look at this as a base 10 equation, then it would be product of sums. Okay? Any questions about what I just did? Now, here's the real key thing. Let's go back to what we started with. Remember, the first thing we did is we wrote, because we wanted POS for E, we started with SOP for not E, right? Then I did the double not, or I did the not on each side. That was part of the derivation, right? But if I look at what I started with, right? We started with this, right? We started with SOP for not E, right? You got it from where the zeros are on the truth table. Now compare what we started with to what we ended up with. Can you see how you can quickly go from here to here or the other direction? How could you do it? How could you go from here to here without doing the Morgan's part, not doing the derivation? Right, you invert every variable, and what else? Exactly. See, to go here to here, we're inverting all the variables. We're changing ands to ors, and we're changing ors to ands, right? And it doesn't matter whether you go in this direction or that direction, right? We started with SOP and got POS, but if you had POS, you could go the other way, right? If you go the other way, it's the same thing. You invert everything, ors to ands to ors. Okay, so I show you the derivation here in class just so you don't think it's magic that, to get one of these, you got to start with the opposite. You see, that's the reason you have to start with not the SOP to get POS for E, because everything inverts. Okay, a common mistake is that instead of starting with SOP for not E to get POS for E, people start with SOP for E. But if you do that, you're going to get POS for not E. Okay, because again, everything inverts. And ands go to ors and ors go to ands. Okay? Now, you may wonder, well, so what? Like, why have these different forms? Well, the reason why it's good to know both of these is because in certain cases, depending on the truth table that you start with, in certain cases, one of these forms will give you less number of gates. Because remember, these two equations are logically equivalent. They're going to give you the same truth table, right? They came from the same truth table. Okay, so sometimes, an SOP will give you less gates than a POS. Other times, a POS will give you less gates than an SOP. Okay, so it's good to know both forms, because knowing both forms, you can get the most efficient logic circuit to give you the same result, which is the truth table. Okay, so we're right at the top of the hour. Let's go ahead and just take a 5-minute break. When you come back from the break, it's only going to take me maybe 15 minutes to go through the rest, but I think it's a good time to take a short break. If you got to go to the restroom or you want to get a drink of water or something, and then I'll pick up again in 5 minutes.
So SOP for the ones and give us review, like,
Well,
good way to think about it.
Well, you can have SOP for E and also SOP for not E, right? Because remember, that's what we did here, right? We started with
Yeah, but POS I mean, for.
Well, to get POS for E, you want to start with SOP for not E, because everything inverts. And you're right, not E comes from zeros. But if you wanted POS for not E, you would start with SOP for E. So you would start with the ones, because again, anytime you go between the two forms, everything inverts.
So you always start with SOP.
Well, well, always start with SOP if you're starting with like a truth table. But you're gonna see in the activity that I have, the second part of the activity, and we're gonna talk about this after the break, but I'm gonna write a circuit diagram for each one of these forms. And like in the activity, I give you a diagram that's a POS. So you gotta start with POS in that case. But again, if you start with POS, you
Yeah.
can go,
Yeah, exactly.
yeah, you can go either direction. So
Okay.
yeah, this example, I went SOP to POS, but you can also go the other way. Okay.
So these are the warnings I got.
Did you send me the email?
I did, but that was like, the warnings when before I go into the base. But this one is like, what's I put it into?
Okay,
The
so you
hardware,
get,
I got this, but on your.
Yeah, it's a time.
The timing warnings,
uh,
does it work on it? But
yeah, that's a modification I'll have to make. At one time, I was telling people to check for timing because that can be an issue in the next class. But I decided as far as this class goes, and in fact, I wrote it up. Yeah. Okay, definitely can't have any. Right, no warning that. If you have other warnings, like when you have this line, your thing works, then consider it constant. If not, it's a little explain. I mean, that's good for this class, because in this class, timing is not. When you take the class, there. It usually has nothing to do with, in the constraints file, there's like a couple of lines with a spot, although they should be. Yeah, they should be, they're not. Using the clock. We will use the clock later. Yeah, I'm not sure why at this point, but for the purposes of this class, I'm.
This is.
yeah, and then.
Yeah, they're here. Yeah.
I don't think. Yeah, there's like. Next one. Sorry. All right. Yeah.
Okay, what's your name? Okay, right, I'm gonna add on.
I just wanted to let you.
Okay, well. See how it's. I mean, if all your threes, six, I'm gonna go with the same thing. And again, you don't, I mean, I make a report.
Okay, yeah, I'll try.
Oh, that's good. Okay, so you have some school coming.
Yeah, I think.
Okay. Okay. The Timmy Chin. Oh, here, okay. Okay, I saw somebody come. And then, is it Michael? I think I saw him come. His last name is D.I. Are you Michael or Anthony? Is your last name D.I.? What's your first name? Yeah. Andrew. Okay, thanks. Okay, so let's go ahead and pick up again. Like I said, it should only be like about 15 minutes for me to finish this. Okay, so the next thing I want to show you is how to get a circuit diagram for each one of these Boolean expressions. Okay, so let's start with the SOP. See, I can go directly from this Boolean equation to a logic diagram that has the logic table. So look, this term here, right, is not C ANDed with G, ANDed with not S. So that's going to be an AND gate. You see, if I take an AND gate, and it's 3 inputs. One of the inputs is just going to be G. The other one's going to have the input inverted, so I'd have a inverter. Right, like C on this side, not C on the other side of the inverter. And then same sort of thing here for not S, right? I'd have S on this side, not S on that side. So you see this AND gate would give me, at the output, it would give me this term. And then I'm going to need an AND gate for each of these remaining terms. So I'm going to have a total of 4 AND gates. Right? 4 AND gates. Now, do you want me to write in the variables, or do you get the idea? You know, like for this one here, again, I have an inverter to invert C. And then I just have G and S. Right, so the output would be not C, G, S. And same sort of thing to get this term here, this term here. You could fill in the rest, right? Okay, so each AND gate gives me a term, and then each one of these terms is OR, right? And the terms are at the output of the AND gate, so I would just take the output of these AND gates and feed it into one OR gate. So you see, I'd have an OR gate where these AND gate outputs go. And then at the output of this OR gate, I would have this equation, right? Because it would take this term, or it with this term, or it with this term, or it with this term. Okay? So you see an SOP circuit diagram, you'll have multiple AND gates, right? Because each AND gate gives you a term. And it will have one OR gate because those terms are all ORed together. Does that make sense? All right, if that made sense, what would the circuit diagram for a POS look like? Yeah, it's just the opposite of this, right? Because each term is an OR gate, right? See how each of these is being ORed together? Right, so I'd have C, G, and S being ORed together. And then here we have C, E, and S gets inverted. Right? So here at this output, I have C ORed with G, ORed with S. Here I have C ORed with G, ORed with not S. Right? I'd have 2 more OR gates. Right? Because each OR gate gives me a term, and then those terms are ANDed. Then I would have an AND gate that the outputs of the OR gate go into. And then at the output of the AND gate, I have this expression here, E. Okay. So you see SOP, you have multiple AND gates, 1 OR gate. POS, you have multiple OR gates, 1 AND gate. They're just kind of like opposite each other. Now, in this truth table, because we had an equal number of 1s and an equal number of 0s, that's why we've got the same number of gates for each form. But I think you can imagine that if we had more 1s than 0s, well, then our circuitry for the POS would be less than what we had for the SOP, right? Or if we had more 0s, then the POS would be a larger circuit than the SOP. So you see, that's why it's good to know both forms, right? Because unless your truth table is symmetrical, meaning you have the same number of 0s and 1s, one form is going to give you less circuitry than the other. Okay, and again, these are logically equivalent, so this circuit and this circuit, it gives us the same truth table. Gives us the same result, they're the same, logical. Okay, so that's the circuit diagrams. Okay, next thing, timing diagram. We did all this. Okay, and I had this started here ahead of time, so I'll give you a moment to copy this down, but we're gonna look at this example timing diagram here. And it's very important in this class to understand timing diagrams because that's how you verify your lab designs in Vivado. Okay, when you run a simulation in Vivado, it makes a timing diagram. And then you look at that timing diagram to verify that it's giving you the truth table that you intended, right? If your simulation is giving you the same data as the truth table does, well, then you know your design is good, that it simulates successfully. And then it's okay to generate a bit file, download it to your board, and then you're testing the design on your board using switches and an LED, right? An LED for visual output, switches to determine your inputs, right? 0, one position of the switch, 1, the other position of the switch. Okay, so you know, I'll probably mention this a few times, especially at the beginning of this quarter, but make sure when you make your video to demonstrate that your lab design is working on the board, make sure you got good resolution, that the switches, the position of the switches can be seen, that the LED, whether it's lit or not, can be seen, because I don't grade the lab work that you submit. I have student graders that do that. You know, I'll be grading the midterm, I'll be grading the final project, but I have students that will grade your lab work. So make sure, you know, you're following the lab criteria that I have on Canvas, and make sure when you make the video that things can be seen. You know, make sure like your simulation, you can actually see the results of the simulation. I can't tell you how many times people lose points on a simulation because they turn one in, but the resolution's bad. Like you can't see what the inputs are. You can't, you know, and if a grader can't see what you've done, you don't get credit for it. So, you know, make the grader happy. Okay. All right, but let's take a look at this timing diagram. Now, the reason I made it green, I did that on purpose. That's because in Vivado, the waveforms, when they're a good waveform, it'll be green. At least it defaults to green. You can change the colors of the waveforms, but as long as you don't change the color of the waveforms, when the waveform doesn't have like a gross mistake, it'll be green. If your waveform defaults to either blue or red, that means something's really wrong. Usually it means like something's not connected right or something's not declared right, okay? But your simulation timing diagram being green, that's not enough to say it's okay, okay? Because it can be green and still have an error. It's just going to be a gross error, okay? Because what you want to do to make sure that your timing diagram, you know, is good, that verifies the truth table that you intend, you want to do the following. See, a timing diagram is just showing you inputs and outputs as time progresses. So when you look at a timing diagram, furthest to the left, that's your T equal to 0. Okay, that's your starting point. And as you go left to right, time progresses. So if we look here, okay, during this part of the timing diagram, see all the inputs are 0. So if my design is working, and we're using this truth table as an example, well, my output E should also be 0. Okay, so if at that time when all the inputs are 0, your output is 0, that's good. Okay, then you can see here at this time, this input changes. So now I have a different combination of inputs, right? It's 0, 0, 1, where S is 1. So again, if my design is good, I should have an output of 0. So this should stay 0. Should stay 0, and then it changes here. Right, during this time, S is 0, G is 1, C is 0. So that's this row of the truth table. So again, if my design is working, E output should be a 1 during that combination of input. Okay, and you just keep going that. In your timing diagram, when you have this combination, the output should be what's in the truth table. So for all these combinations, you should have the same output in your timing diagram as you do in your truth table.
Is there a reason you did S first, give you a timing diagram?
Well, it doesn't matter what order this is in. Like I could change the order and we'd still figure it out the same way. But the reason I did it this way is just because on the top, I put the variable that changes the most. To see how S changes the most, it goes 0, 1, 0, 1, 0, 1, 0, 1. And G goes the second most, and then S changes the least most. So that's just the way I like to do it. I like to put the one that changes the most up top, and now I'll put the one that changes the least on the bottom. It just makes it easier for me to draw because I don't know if you've noticed here, but see, I drew this one as 8 pulses. Then this next waveform, see how I only change it when this one is going high to low. So you see, I change it here when it's high to low, then I change it here when it's high to low, and I change it. See, that's an easy way to get half the number of pulses. Yeah, I started with 8, then I got 4, then I got 2, and that's just so it's just more easily seen. You know, I could make it not so nice, but you know, anyway. Yeah, but again, you could mix these up, and you would still verify it the same way. Okay. So again, this is what you need to do when you're, you know, verifying your simulations on Vivado. You're going to have a timing diagram like this, and you got to look. And actually, it's pretty nice in Vivado because there's a cursor, like there's like a yellow cursor that you can just click. Wherever you click with your mouse on the wave, on the timing diagram, it will put like a cursor. You know, I drew these dashed lines, but you'll have like a straight yellow line. And where that line passes through, over in the window to the left, it will show you the value. You know, like 0, 0, 0, 0. You know, when we go to the next one, 0, 0, 4, 0, 1, 0, and so on. Okay. Yeah, when you do your simulation on Vivado, if there's anything that you have a question about, get those questions answered early. Because every lab, you got to do a simulation. When you take a follow-on class, I might have mentioned before, but I'll say it again, for the first 8 weeks, that's all you're doing in that class is you're doing simulations. You don't download to the board until the very end of that class. Now, in this class, we have you download every week. Okay, but and don't skip the simulations. You know, sometimes students will, some students will skip the simulation, just download to the board, you know, and test it on the board. But again, get used to the simulation. It's the most efficient way, and you're going to know it, or you're going to have to know it for CP 233 anyway. Okay. All right. So that's well. Any questions on that before we move on? There's just 2 more things here. One is a black box diagram, and a black box diagram. I guess I should have moved this a little bit. There we go. The black box diagram, as the name implies, is just a box. Okay, so we show it as a square. And its purpose is just to show the main inputs and the main outputs of whatever you're designing. So, you know, if this, you know, my appetite for those ingredients, if that's our design, then, you know, we have 3 inputs, C, G, and S. We just got 1 output. You know, so your black box diagram for lab 0, you know, it's going to have 3 inputs. I think in my video, I just labeled them A, B, C, and then 1 output. I forget what I use as the output, but you know, you just have the 1 output. Okay. Now, for the first couple of labs, yeah, lab 0 and lab 1, because the designs are, you know, basic, because you know you're learning the software at this point. You know, it's okay to use, you know, non-descriptive inputs and outputs like I did, just single variable. But when we get to designs, and I think this will start with lab 2, eventually we're going to get to designs that have multiple modules, right? Instead of just 1 black box diagram, you're going to have a bigger black box diagram that contains what we call individual modules. So when we get to that point, you would want to be more descriptive with your inputs and outputs. Like you wouldn't want to call for each one of these, you wouldn't want to call all your inputs the same and all your outputs the same. And that's because when you go to look at a timing diagram, well, if all your inputs and all your outputs, so all your different modules are named the same, it's going to make it really hard for you when you look at a timing diagram to know, oh, which A is this? Is it the A of this? Is it the A of that? You know, so, you know, if this was say this was a module that was doing something called decoding, which we're going to talk about later on in the course. Let's say that was a decoder. Instead of just calling this input A, you might want to do DEC_A. You know, and like if this thing's called like a multiplier or something, you might want to call that, you know, MULT_A. So you know it's that input to this module. This is especially important when you take CP233, because when you build the microprocessor in CP233, you're going to have like a dozen or more of these modules. And if you just call everything, you know, all inputs A and B and all outputs Q or F, but when you look at the timing diagram, you're going to have like, you know, 30 waveforms. And there's going to be like 6 of them that are named the same. You're going to be like, oh, wait, you know, which module is this from? So anyway, the descriptive names is just a way to do like easy bookkeeping, if you will. Okay. All right, so that's all a black box diagram. It's also a black box diagram. You give it a name, you know, like I could call this GP for my name _ APP for appetite or something. You know, for lab 0, you could just name it lab 0 if you wanted. Okay, I don't think I have you, well, I know that I don't have you turn in a black box diagram for the labs, but you should make one for all your labs just for your own notes. Because knowing the black box diagram, that will tell you what your main inputs and main outputs are. So at the very beginning of Avado, when you're declaring your inputs and outputs, you just got to look at your black box diagram. Okay. All right. Last thing is how you would write SOP and POS in System Verilog. Okay. So let's see. Let's look at this SOP. Okay, and System Verilog. Okay, so you're going to have to do this for lab 0. Okay, we want to write this SOP Boolean equation as a System Verilog equation. Well, the way you would do that is we use what's called the assign. You would type assign, and then you put the output of E, and then equals. Okay, then what I would do is in parentheses, we write this term. Now, in System Verilog, when you're doing a Boolean equation, to not a variable, you use the tilde, okay, which is the little squiggly line. When you look at a keyboard, the tilde is to the left of the 1 key. So you'd have to do like a shift and then hit the key that's to the left of the 1. There's that little squiggly. Yeah. Everyone know what a tilde is? Because sometimes people use a dash, and a dash isn't going to work. Okay, it's going to be the squiggly, the tilde. So you would put tilde. See, we're looking at this one here. So tilde C, that's not C. Now, in System Verilog, to do and, okay, to and something, you can't leave a space. Okay, because I think it will multiply it. Because you can do multiplication in Verilog. What you have to use for the and is the ampersand symbol. Okay, ampersand, that's the symbol that's above the 7 on your keyboard. So you have to do a shift 7. Okay, so then you would put G next, and then ampersand again, and then tilde S. Okay, so you see this here is the Verilog with this. You see the tilde is the not, the ampersand is ending. Okay, so you would do that for each of the 4 terms, right? So you're going to have 4 terms that, you know, you follow this. It's just, you know, you just gotta make it this term, this term, and this term, right? Now the or symbol, right? Because we got to or these terms together. The or symbol in System Verilog is the vertical line. You don't use plus because in System Verilog, a plus is actually addition. So it's the vertical line. So it's above the slash, the backslash. So you have to do like a shift backslash. Okay, so it's a vertical line. So you have to have a vertical line between all of these for the ors. And then you end it with a semicolon. Okay, you end a line in System Verilog with a semicolon. All right, now POS, same idea, right? POS in System Verilog. and you do a sign again. Now for lab 0, you're just doing one equation, you're just doing SOP, right? You're just doing the same equation that I did in my video. But here, in parentheses, you can put, for this term here, it would just be C, vertical line, G, vertical line, S, then you'd have that ampersand, between the terms. Okay, so yeah, it's just in system Verilog. For and, we use ampersand. For not, when it's a Boolean equation, we use tilde. And for or, we use a vertical line. Okay. All right, so unless there's questions, that's all that I was going to talk about for lecture today. So the remainder of the time, first, you want to do the activity. Again, there should be enough activity sheet for each person at the table. If not, let me know. I have extras. But just like last week and for all this quarter, you just pass one in for your table. And then when you're done with the activity, work on your lab 0. And remember, lab 0 is due tomorrow night. So if you don't finish today, you still have time to finish because it's due midnight tomorrow.